The 1940s promised a revolution in locomotive reliability. Railroads unveiled experimental machines incorporating cutting-edge technology, streamlined designs, and bold engineering innovations that were supposed to run forever with minimal maintenance. Repair shops would become nearly obsolete, they claimed. These locomotives would never break down. What actually happened was the exact opposite. The 1940s became steam's final desperate gamble, producing some of the most spectacular mechanical disasters in railroad history. These weren't just failures, they were engineering catastrophes that helped kill the very technology they were meant to save. The irony runs deeper than you might imagine. While salesmen promised reliability, these machines spent more time in repair shops than on main lines. While marketing touted breakthrough designs, crews fought mechanical nightmares on every run. While management dreamed of defeating diesel domination, they were actually funding steam's funeral. The story of why these locomotives supposedly never broke down is really the story of why they never stopped breaking down. The Atlantic Coastline R1 arrived in 1938, carrying Baldwin's grand promise that duplex power could finally work in revenue service. It didn't. This ambitious 4444 was supposed to handle heavy passenger trains with the smooth divided drive that would revolutionize railroading. Instead, it became a rolling lesson in why some ideas should stay permanently confined to drawing boards, no matter how elegant they look in theory. Baldwin pitched the R1 as the answer to every railroad's prayers. Two sets of driving wheels under a rigid frame, each powered by its own cylinders, would distribute power more evenly than traditional designs. Lighter reciprocating parts promised reduced track wear. Higher speeds would come naturally from the balanced configuration. The Atlantic Coastline bought the sales pitch and waited for their revolutionary locomotive. What they got was a machine that fought its crews from the moment steam entered the cylinders. The R1's fundamental problem was weight distribution, though nobody realized this until it was too late. With two sets of driving wheels under a rigid frame, getting equal adhesion proved impossible in practice. The front drivers would slip violently, while rear drivers grabbed with crushing force, or vice versa. Engineers spent more time fighting wheel slip than actually running trains, constantly modulating throttle in a futile attempt to find the sweet spot that would make both driver sets work together. That sweet spot didn't exist. Making matters significantly worse, Baldwin had mounted the backward-facing rear cylinders close to the firebox. This seemed clever on paper, keeping the locomotive shorter and theoretically balancing weight better. In reality, it created maintenance nightmares nobody had anticipated. Those cylinders ran hot constantly, baked by firebox heat that had nowhere else to go. Ash and grit infiltrated every seal, every bearing surface, every moving part. The components wore out faster than maintenance crews could replace them. Steam pipes ran so ridiculously long from boiler to rear cylinders that pressure dropped significantly before reaching the pistons. The locomotive theoretically produced substantial horsepower at the throttle, but delivered far less to the rails. The math looked good in Baldwin's promotional literature. That decision would spawn even more spectacular disasters down the line, proving that sometimes the railroad industry's institutional memory worked about as well as the locomotives it kept building. Pennsylvania Railroad's Q1 looked like the future when it emerged from Altoona Works in 1942. Streamlined by legendary designer Raymond Loewy, this imposing 4644 was supposed to prove duplex drive could handle heavy freight service where the R1 had failed in passenger service. Instead, it proved that some fundamental engineering mistakes refused to stay buried, no matter how pretty the shell you wrap around them. The designers mounted the rear cylinders backward, facing the firebox, exactly like the disastrous R1 arrangement. This seemed clever on paper for all the same reasons it seemed clever before. It kept the locomotive shorter. It theoretically balanced weight better. It looked innovative in technical drawings. In reality, it created mechanical nightmares that plagued the Q1 throughout its brief, miserable career. Firebox heat baked those rear cylinders constantly, creating temperatures that destroyed lubrication and warped metal. Ash infiltrated every seal and bearing surface with the persistence of water-finding cracks. Steam pipes stretched so far that pressure dropped dramatically before reaching pistons, wasting energy the locomotive desperately needed for heavy freight hauling. Making matters considerably worse, PRR gave the Q1 passenger-sized 77-inch driving wheels on a freight locomotive. This was like putting racing tires on a dump truck. The large wheels optimized for high speed meant the locomotive struggled with heavy starts and couldn't develop proper tractive effort at low speeds where freight trains needed it most. The firebox, constrained by those backward cylinders, ran too small for sustained hauling. During runs, the Q1 would lose steam pressure as the firebox simply couldn't keep up with demand. Engineers would have to ease off the throttle, losing momentum and time, waiting for pressure to rebuild before attempting to continue. The Q1 taught lessons that Pennsylvania Railroad chose not to fully understand, setting the stage for even more expensive failures. The Baltimore and Ohio's George H. Emerson emerged in 1937 as America's first true duplex locomotive. Nobody at the railroad was particularly proud of it afterward. Built at B&O's Mount Clair shops in Baltimore, this experimental 444 carried the name of the railroad's chief of motive power. Perhaps they should have waited to see if it actually worked before permanently attaching his name to what became a legendary embarrassment. The Emerson borrowed heavily from European experiments, particularly German and French designs that had shown promise in testing. It featured two sets of driving wheels under a rigid frame, each powered by its own cylinders, implementing the duplex concept that looked so elegant in theory. The theory was genuinely elegant, which is why so many engineers fell for it. Smaller cylinders and lighter reciprocating parts would reduce the hammer blow that damaged tracks. Dividing power between two drive sets would allow higher speeds without the violent surging of conventional designs. Smooth power delivery would improve ride quality and reduce wear on running gear. In practice, the locomotive fought its crews constantly from the first revenue run. Those rear cylinders, mounted close to the firebox like every other duplex disaster, ran hot and wore out far too quickly. The dual throttle system required engineers to manually balance power between the two driver sets. Getting it wrong meant one set slipped while the other overworked, creating the exact uneven power delivery the design was supposed to eliminate. Getting it right required constant attention and skill that turned routine runs into exhausting battles of concentration. Maintenance crews found critical components buried in hopelessly inaccessible locations. Repairing worn parts required disassembling half the locomotive to reach components that should have been easily accessible. Simple repairs took days instead of hours. Complex repairs became nightmarish projects that consumed shop time and resources. The B&O tested the Emerson for 6 years without ordering additional units, which tells you everything about how well it actually performed. By 1943, it was quietly retired to the scrap line. Having convinced management that duplex power was definitively someone else's problem, B&O chose diesel locomotives for future motive power. The George H. Emerson's failure helped push one of America's most innovative railroads toward abandoning steam entirely, making it a more significant locomotive than its brief service record might suggest. Sometimes failures teach more important lessons than successes, though in this case, the lesson went largely ignored by other railroads who would repeat the same mistakes. When Baldwin pitched duplex power to Pennsylvania Railroad in the late 1930s, they promised a locomotive combining Pacific speed with northern pulling power. PRR Engineering was skeptical, having watched the industry's earlier duplex disasters. Baldwin built the S1 to prove them wrong in the most dramatic way possible. At 140 feet long and weighing over 1 million pounds with tender, it was possibly the largest passenger steam locomotive ever built. It was also far too big to actually be useful, which became apparent almost immediately. The S1's 6-4-4-6 wheel arrangement looked revolutionary in Baldwin's promotional materials. Raymond Loewy's streamlining made it appear to be traveling at speed even when standing still at the station. But beneath that gorgeous shell lurked fundamental flaws that no amount of styling could overcome. The locomotive couldn't navigate most of PRR's network, which was kind of important for a machine meant to haul trains. Turntables couldn't handle its length. Curves threatened derailment on trackage designed for conventional locomotives. PRR was forced to restrict it to just 283 miles between Chicago and Crestline, a pathetically limited territory for such an expensive machine. Wheel slip plagued every single run without exception. With driving wheels, divided between two sets, achieving balanced adhesion proved impossible regardless of what engineers tried. The S1's failure was particularly significant because it showed that even unlimited engineering resources and the best designers couldn't make duplex drive work. If Pennsylvania Railroad, with its massive technical staff, couldn't solve the problems, nobody could. In 1944, Pennsylvania Railroad unveiled something that looked like a conventional steam locomotive, but sounded completely different. The S2 steam turbine made no chuffing sound, just a continuous whoosh as 6,900 horsepower drove wheels through a massive gearbox. It was supposed to combine steam's fuel economy with turbine smoothness, proving that steam could match diesel performance. It achieved neither goal, instead demonstrating why turbines belong in power plants running at constant speeds, not locomotives that must constantly start, stop, and climb grades. The S2 represented the ultimate effort to make coal-fired steam competitive in an age increasingly dominated by diesel-electric power. Built by Baldwin and Westinghouse, it used a direct drive turbine geared to driving axles, eliminating the reciprocating motion that characterized conventional steam power. The gearbox transmitted power with 97% mechanical efficiency, which looked impressive in technical specifications. But turbines have a fatal characteristic that no amount of engineering could overcome. They're incredibly inefficient at low speeds. Above 40 mB/h, the S2 performed magnificently. It could maintain 100 mB/h while pulling heavy passenger trains with fuel economy approaching diesel levels. At cruising speeds, it ran smoothly and quietly, delivering the performance Baldwin had promised. Below 30 interimus, it became a fuel-guzzling monster that horrified everyone who had to operate or maintain it. Starting from rest required the boiler to supply steam at rates it simply couldn't maintain. Pressure plummeted from 310 psi to below 85 psi during acceleration, starving the turbine of the steam it needed. The firebox ran so hot at low speeds that stays cracked repeatedly, requiring constant repairs. Water consumption during acceleration exceeded anything crews had experienced with conventional locomotives. The S2 could drain its tender in miles instead of the hundreds of miles normal locomotives managed. PRR stored the S2 by 1949 after just 5 years of disappointing service. The railroad had invested enormous resources in proving steam turbines could work. The S2 proved the opposite. Turbines belong in power plants running at constant speed, not locomotives facing the endless variations of actual railroad service. The lesson was expensive but clear. Steam's future, if it had one at all, wouldn't come from turbine technology. Pennsylvania Railroad's Q2 class represented everything supposedly learned from the Q1's comprehensive failure. Built between 1944 and 1945, these 4464 freight duplexes were the most powerful, non-articulated steam locomotives ever constructed. They produced nearly 8,000 horsepower at Altoona's test plant. They could haul 125 cars at 50 metri/tidna. And they consumed water like the ocean was running dry, which became their downfall despite all that impressive power. The Q2 fixed the backward cylinder problems that plagued the Q1 by mounting all 4 cylinders ahead of the wheels they drove. The firebox grew large enough for sustained heavy hauling. An automatic wheel slip control system attempted to prevent the violent slipping that characterized earlier duplex disasters. On paper, PRR had finally solved duplex drive's fundamental problems. In practice, they'd created new disasters to replace the old ones. Those Q2s were water hogs on a scale that defied belief. The locomotives consumed water so rapidly that PRR had to install additional water stations along routes they operated. A conventional locomotive might travel 100 miles between water stops. The Q2s needed water every 60 miles, sometimes less under hard running. The automatic wheel slip control system helped, but couldn't eliminate the fundamental adhesion problems inherent in duplex designs. The complex mechanism added another system that could fail, and it failed regularly. When the wheel slip control malfunctioned, the Q2s reverted to the same violent slipping that plagued every other duplex locomotive. Maintenance requirements exceeded anything PRR had experienced with conventional power. All those additional components needed constant attention. The divided drive system doubled the number of parts that could wear out or break. Shop time stretched longer than anticipated. Costs mounted faster than budgets allowed. By 1949, PRR was quietly sidelining the Q2s in favor of diesel locomotives that might produce less peak horsepower, but ran reliably day after day without drama. The Q2s represented steam's last chance to compete on pure performance. They proved that even the most powerful steam locomotives couldn't overcome the fundamental operational advantages of diesel-electric power. Railroads didn't need the most power. They needed reliable, economical power that showed up for work every day. The Q2s, for all their impressive specifications, couldn't deliver that basic requirement. The Chesapeake and Ohio's M1 steam turbine emerged in 1947 as America's other attempt to make turbine power work in steam locomotives. Unlike PRR's S2, which used a direct drive turbine, the M1 employed turbines to drive electric generators that powered traction motors, exactly like a diesel-electric locomotive. It was a coal-burning locomotive with diesel-electric running gear. Only 3 were ever built, and their problems began immediately. Coal dust and ash were the enemies of precision machinery. The turbine blades accumulated deposits that threw them out of balance, creating vibrations that damaged bearings and supports. The generators ran hot under load, requiring cooling systems that added complexity and weight. The traction motors struggled under the sustained loads that steam could provide, a problem diesel electrics didn't face because their prime movers produced less power. Maintenance logs from the era read like horror stories, with crews fighting endless battles against fouled components and overheating systems. At speed, the ride was eerily smooth. No hammer blow from reciprocating rods meant less track damage and a quieter cab. The turbine whispered, while conventional locomotives pounded the rails. Crews appreciated the smooth operation when it worked. But the M1's fatal flaw was economics, the same problem that killed the S2. Turbines operate efficiently at high sustained speeds. Real-world railroading involves constant acceleration, deceleration, stops, and starts. At low speeds, the M1's fuel consumption was catastrophic, burning coal at rates that made dispatchers wince. Every start from rest cost fuel that conventional locomotives used far more efficiently. C&O retired the M1s by 1950 after just 3 years of disappointing service. The railroad had hoped turbine electric drive would combine coal's cheapness with diesel's operational advantages. Instead, they got coal's maintenance headaches combined with diesel's mechanical complexity. The M1 proved that mixing technologies doesn't automatically produce the best of both worlds. Sometimes, you just get the worst of both. The Norfolk and Western's TE1 took a different approach to turbine power, using a coal-fired turbine to generate electricity for motors, but with a more conventional boiler design than C&O's M1. Built in 1954, it arrived too late to save steam, even if it had worked perfectly. It didn't work perfectly. it barely worked at all. N&W was steam's last defender among major American railroads, operating steam locomotives profitably into the 1950s, while other railroads dieselized. The TE1 was supposed to prove that modern turbine technology could extend steam's viability into the diesel era. Instead, it proved that timing matters as much as technology. By 1954, diesel builders had refined their products through years of experience. Steam turbines were starting from scratch, trying to compete with mature technology. The TE1 suffered all the problems of earlier turbine experiments, plus new ones unique to its later arrival. Maintenance was nightmarish. Parts were custom-made and expensive. No standardization existed because only one locomotive of its type existed. When something broke, crews had to fabricate repairs because no spare parts inventory existed. The turbine itself ran inconsistently, performing well one day and poorly the next for reasons nobody could consistently diagnose. N&W stored the TE1 after minimal testing, never putting it into regular service. The railroad that had defended steam longest finally admitted that diesel-electric power was the future. The TE1's failure marked the end of American experimentation with steam. Turbine locomotives. No railroad would try again. The concept was dead, killed by the same fundamental problems that plagued every turbine experiment. Efficiency only at sustained high speeds, complexity that defied maintenance, and timing that arrived too late to matter. The Union Pacific's Big Boy class illustrates why even successful steam locomotives lost to diesels. These massive 4884 articulated locomotives worked exactly as designed, hauling heavy freight over Sherman Hill with impressive reliability. They still lost to diesel power because Big Boys required huge crews, extensive servicing every 150 miles, and specialized maintenance facilities. Union Pacific calculated that diesels cost less to operate, despite the Big Boys' proven performance. By 1959, even locomotives this successful couldn't compete with diesel economics. The Erie Railroad's Triplex locomotives represented the pinnacle of more is better thinking applied to steam power. Built between 1914 and 1916 by the American Locomotive Company, these two 888-2 behemoths featured 3 engine units, one in front, one in back, and one underneath the tender. On paper, this arrangement provided 160,000 pounds of tractive effort, enough to move mountains. The Erie needed exactly that kind of power for steep grades through New York's southern tier. Reality proved less cooperative than paper calculations suggested. Like all triplex designs, the single boiler couldn't keep pace with steam demands from 3 engine sets operating simultaneously at anything above a crawl. The laws of thermodynamics don't care how many cylinders you install. A boiler can only generate steam at its design rate. Asking 3 engines to share steam designed for 2 meant all 3 operated below their potential. Crews nicknamed them yard rippers because they excelled at pulling long trains out of terminals where low speeds didn't matter. On the main line where sustained power mattered, they failed comprehensively. The boiler simply couldn't maintain pressure. Trains would slow as steam pressure dropped, forcing engineers to ease off the throttle and wait for the boiler to catch up. The 3rd engine unit underneath the tender created additional problems. As the tender's weight decreased with coal and water consumption, weight distribution changed continuously. The tender-mounted engine fought against the other engine units rather than working with them. Traction varied unpredictably as fuel and water loads changed. All 3 Erie triplexes were eventually rebuilt into more conventional configurations, proving that the original design was fundamentally flawed. The triplex concept died on those grades, a bold idea that simply couldn't overcome the physics of steam generation. More engines don't help if you can't feed them steam. The Virginian Railway's massive triplex took the 3-engine concept even further, producing what remains the largest steam locomotive ever built by several measurements. This 2.884 monster stretched over 100 feet long and weighed 684,000 pounds without tender. The single boiler feeding 3 engine sets created catastrophic problems. Steam pressure dropped under load. The locomotive could start heavy trains, but couldn't sustain speed once moving. Crews reported it ran out of steam before running out of track. The Virginian Triplex lasted barely 5 years before being broken up for scrap in 1920. The locomotive represents the absolute extreme of articulated steam power, the point where ambition overwhelmed physics so completely that the result was comical. The Pennsylvania Railroad's T1 class represented PRR's final attempt to make duplex drive work after the disasters of the S1, Q1, and Q2. Built between 1942 and 1946, these 4-4-4-4 passenger locomotives incorporated everything supposedly learned from previous failures. They failed anyway, proving that some fundamental design concepts simply don't work, no matter how much you refine them. The T1s were beautiful machines, streamlined by Raymond Loewy in shark-nose styling that became iconic. They were fast, reportedly capable of exceeding 100 maperettes. They were powerful, rated at 6,550 horsepower. They were also unreliable, maintenance-intensive, and prone to the same wheel slip problems that plagued every other duplex locomotive. The divided drive system that was supposed to eliminate wheel slip actually made it worse. With 4 driving axles arranged in 2 separate sets, achieving balanced adhesion remained impossible. One set would slip while the other grabbed. The automatic wheel slip control systems helped when they worked, but added complexity that created new failure modes. Crews developed love-hate relationships with T1s. When everything worked, they were magnificent machines capable of remarkable performance. When anything failed, they became frustrating nightmares that couldn't be trusted. The inconsistency made them unsuitable for reliable service. PRR needed locomotives. That worked every time, not machines that were spectacular on good days and disasters on bad days. By 1952, PRR was retiring T1s after barely a decade of service, replacing them with diesel locomotives that might be less exciting but showed up for work reliably. The T1 represented steam's last chance to compete with diesel on passenger trains. The failure sealed steam's fate on PRR and influenced decisions across the industry. The New York Central's Niagara class represents successful steam design, locomotives that worked as intended and served reliably. So why mention them here? Because even successful steam locomotives like the Niagaras lost to diesel power, demonstrating that steam's problem wasn't just bad engineering. The Niagaras were magnificent 4.8-4 locomotives producing 6,600 horsepower and capable of sustained high speeds. They hauled NYC's premier passenger trains reliably. Crews loved them. They still got scrapped by 1956, replaced by diesels. NYC calculated that diesels cost less per ton-mile despite higher initial purchase prices. The savings came from reduced labor, simplified servicing, better availability, and longer operating ranges. If locomotives this good couldn't survive, the experimental disasters described earlier never had a chance. Every locomotive discussed here failed for specific reasons. Bad weight distribution, inadequate boilers, complex controls, turbine inefficiency at low speeds, excessive maintenance requirements, poor timing, or simple bad luck. But their collective failure tells a larger story about engineering hubris meeting economic reality in the 1940s. These experiments weren't stupid. Many incorporated genuinely brilliant innovations that would later appear in successful diesel and electric locomotives. Electric traction motors, automatic controls, streamlined car bodies, advanced metallurgy. The engineers weren't fools. They were desperate. They saw diesel locomotives threatening steam's dominance and tried everything imaginable to respond. Some attempts were more realistic than others, but all shared the same fundamental problem. They were trying to fix steam's inherent disadvantages through engineering brilliance. No amount of brilliance could overcome thermodynamics. Diesel locomotives offered something steam never could.
Crews nicknamed her the Nightmare because keeping her running demanded expertise that simply didn't exist in most engine sheds. The W1 spent more time in shops than on main lines. Eventually, the railway gave up and rebuilt her with a conventional boiler, ending one of the most ambitious experiments in British steam history. Coal-fired boilers produced the steam that spun turbines, which drove generators, which powered electric traction motors. In 1944, the Pennsylvania Railroad unveiled a locomotive that sounded like the future. The S2 was powered not by pistons, but by a steam turbine connected directly to the driving wheels. No rods, no reciprocating motion, just smooth turbine power spinning the drivers at speeds up to 100 miles per hour. At low speeds, the S2's fuel consumption was catastrophic, burning coal at rates that made dispatchers wince. The John Henry spent more time in the Roanoke shops than on the rails. Less than 3 years after its debut, Norfolk and Western retired their turbine and ordered diesels. The railroad that had sworn allegiance to steam finally surrendered. The John Henry was scrapped, and with it died the last hope that steam technology could evolve fast enough to survive. Sometimes the legend loses to the machine. Number 2. Southern Pacific Cab Forward AC-12. When Southern Pacific finally dieselized in the 1950s, the cab forwards were retired, designed the streamlined shroud that made the S1 look like it was moving at 100 miles per hour while standing still. And it could actually do that. Reports suggest the S1 achieved speeds approaching 140 miles per hour during testing. The engine was displayed at the 1939 New York World's Fair, where millions watched its massive drivers spin under steam power on special rollers. But the S1 size was also its weakness. It could not negotiate curves on most Pennsylvania railroad lines.
The concept promised to eliminate the notorious hammer blow effect that destroyed track, reduce moving mass by over 40%, and allow steam locomotives to operate smoothly at speeds exceeding 150 miles per hour. British Railways tested a prototype on a modified Class 9F and immediately banned further development. The official reason was complexity and maintenance concerns. The real reason was that British Railways had already committed to dieselization, and this system threatened to make steam locomotives competitive again. Modern finite element analysis proves Bose was right on every count. The design would have worked brilliantly, distributing forces through the mechanism in ways that actually reduced bearing stress compared to conventional systems. Computer modeling shows the Bose drive could have extended steam locomotive life by 20 years minimum. Engineers who have studied the archived drawings call it one of the greatest missed opportunities in locomotive history. The system that could have saved steam power was killed by bureaucrats who had already decided its fate. Number 19. The Giesel oblong ejector. This meant more power for less coal consumption. Multiple European railways installed Giesel ejectors experimentally in the early 60s, then quietly removed them when diesel manufacturers started complaining about unfair competition. The objection was never technical. The objection was that it made steam too efficient. Modern computational fluid dynamics analysis confirms what Giesel knew through intuition and testing, recovering heat that conventional designs simply blew into the atmosphere. British Railways built 10 locomotives with Franco-Crosty boilers in 1955, then banned any further construction in 1962 after crews complained about smoke deflection problems and maintenance difficulties. The smoke issue was real but solvable. The maintenance concern was deliberately exaggerated by depot workers who wanted simpler diesel assignments. What everyone missed was the fundamental efficiency gain, allowing each unit to optimize power delivery independently. Deutsche Bundesbahn rejected the proposal outright, citing excessive development costs and questioning why anyone would invest in steam technology when diesel-electric locomotives were clearly the future. The decision seemed rational at the time, could operate safely within locomotive clearances. The locomotive would have required refueling only once every 18 months and would have had effectively unlimited range. The Soviet Railway Ministry banned the project before a prototype was constructed, citing radiation concerns and international treaty complications. The official reasoning made sense, but modern analysis suggests the real reason was simpler. The design was too far ahead of available shielding materials and control systems. What makes this banned design genius in retrospect is that the fundamental concept was completely sound. Modern engineers looking at Chapelon's calculations recognize the tragic irony. The ban condemned Irish railways to permanent dependence on imported diesel fuel when a genius indigenous solution was available. Number 13. The gyroscopic stabilization system. If Swiss Federal Railways had approved development, Switzerland might have pioneered high-speed rail technology a decade before Japan's Shinkansen demonstrated the concept to the world. Number 12. Sentinel Kamati Uniflow engine. The Sentinel company's final design before their locomotive division closed proposed a radically different approach to steam power. Instead of conventional double-acting cylinders where steam pushed pistons in both directions, the Uniflow design allowed steam to enter only at one end while exhausting through ports in the cylinder walls. This eliminated the need for complex valve gear entirely, replacing it with simple poppet valves that opened and closed based purely on piston position.
The system could recover up to 90% of the water used, extending range to nearly 500 miles between stops. Only 90 Class 25 condensing locomotives were ever built. The complexity was staggering. 6 steam-driven fans forced air through miles of radiator tubing while the locomotive thundered across the desert. Maintenance crews battled scale buildup and tube failures constantly. The condensing equipment added tons of weight and required specialized knowledge few possessed.
Most remarkably, the independent engine control system anticipated by 4 decades the distributed power concepts that modern freight railroads now consider essential. Henschel was proposing in 1960 what Union Pacific would not fully implement until the late 1990s. The ban meant Germany missed a technological leap that might have kept steam competitive for high-speed passenger service. Number 16. Soviet-type P-38 nuclear steam locomotive. In 1964, Soviet engineers proposed a locomotive powered by a small nuclear reactor instead of a coal fire, generating steam for conventional reciprocating machinery. The concept was not as insane as it sounds. Reactor technology had advanced to the point where a compact, heavily shielded unit. Swiss engineers in 1963 proposed installing large gyroscopes in locomotive tenders to actively stabilize trains at high speeds, allowing safe operation at velocities that would make conventional designs derail. The system used servo-controlled gyroscopes spinning at 12,000 RPM to detect and counteract lateral oscillations before they could develop into dangerous hunting motion. Swiss Federal Railways rejected the design as unnecessarily complex and potentially dangerous if the gyroscope systems failed. The decision seemed prudent at the time. It now seems absurdly conservative. Modern high-speed trains use active suspension systems based on exactly this principle. The electronics differ, but the fundamental concept of using powered stabilization to counteract lateral motion is now considered essential for any train operating above 120 miles per hour. The Swiss gyroscopic system would have worked perfectly with 1960s technology. Failure modes that concerned regulators could have been managed through redundancy and fail-safe designs. Engineers now recognize this as a classic case of regulatory caution killing innovation. Current generation compact nuclear reactors prove that small-scale nuclear steam generation is not only possible but practical for mobile applications. The Navy has operated nuclear-powered vessels for 7 decades using essentially this exact concept. The only real barrier in 1964 was materials science, not physics. If the Soviet Union had pursued development for another decade, improvements in radiation shielding would have made the design viable. Engineers now recognize this as a missed opportunity to create a zero-emissions, ultra-long-range locomotive that would have revolutionized freight operations. Number 15. The Chaperon-Livio double compound system. André Chapelon's genius was legendary, but his final design before retirement pushed too far even for his admirers. The double compound system used 4 stages of expansion instead of the conventional 2, extracting maximum energy from steam through progressive re-expansion in increasingly larger cylinders. French National Railways tested a modified 241P with this arrangement in 1962 and documented a 23% improvement in thermal efficiency. They banned any further development anyway because the system was simply too complex. Crews could not understand it, maintenance personnel could not service it, and management could not justify the additional cost when diesels promised simplicity. The double compound system represented the absolute theoretical maximum efficiency achievable with reciprocating steam technology, and French railways abandoned it right when fuel costs were about to skyrocket in the 1970s. The design used direct turbine drive instead of reciprocating engines, promising higher efficiency and reduced maintenance. Chorus Impair Ariane evaluated the proposal for 2 years, then banned any further development, officially because turbine technology was unproven for rail applications. The real reason was that turbine locomotives required specialized manufacturing capabilities that Ireland did not possess. Building the first unit would have required international partnerships that politicians found politically unpalatable. Modern gas turbine technology proves the concept was entirely viable. Contemporary turbine electric. Locomotives demonstrate that direct turbine drive offers significant advantages over reciprocating steam engines. The peat fuel system was equally sound, as current peat-burning power stations throughout Ireland confirm. Engineers now recognize that CIE abandoned a design that would have given Ireland fuel-independent rail transport using domestic resources. Computer simulations confirm that Chapelon's system would have delivered performance matching early diesel-electric locomotives while burning substantially less fuel. The complexity that seemed like a fatal flaw was actually manageable with proper training. Railroads chose immediate convenience over long-term efficiency and banned a system that might have changed transportation history. Number 14. The turf burner turbine system. Irish engineers in 1961 proposed a steam turbine locomotive burning compressed peat instead of coal or oil. Ireland had massive peat deposits, but no oil and minimal coal resources, making fuel independence strategically vital. Austrian engineer Adolf Giesel created what looked like a rectangular garbage chute instead of a traditional smokestack, and railroads hated it on sight. The design challenged over a century of aesthetic tradition with brutal functionality. But here's what they missed. The oblong ejector improved efficiency by up to 15% through superior gas flow dynamics. The elongated shape created multiple smaller exhaust streams instead of one large blast, optimizing draft while minimizing back pressure on the pistons. It now looks catastrophically short-sighted. Engineering analysis of the preserved drawings reveals a machine that would have been capable of sustained 130 mile/hour operation while burning cheaper heavy fuel oil instead of coal. The articulated design distributed weight more evenly than conventional locomotives, reducing track wear substantially. Modern stress analysis shows the streamlined body would have protected running gear from debris while significantly reducing drag. Turnkey simplicity. A diesel started with the push of a button. It required no fire building, no water treatment, no ash disposal. 2 men could operate what steam needed 5. Maintenance intervals stretched from days to weeks. Fuel efficiency remained constant, regardless of speed. Diesels just worked day after day, without drama or heroics. Steam's fundamental problem wasn't technology, it was thermodynamics. Even perfect steam locomotives waste 70% of fuel energy as heat. Diesels waste only 30%. No engineering breakthrough could overcome that basic physics. The laws of thermodynamics don't negotiate. These 20 locomotive stories weren't just individual failures, they were steam's death throes, each one proving that the future belonged to internal combustion, no matter how hard engineers fought against the inevitable. The 1940s experiments represented steam's final, desperate gamble against diesel domination. They lost that gamble comprehensively, helping to kill the very technology they were meant to save. The irony of locomotives that supposedly never broke down actually spending more time broken than working is perhaps the perfect metaphor for steam's final decade. Promise exceeded performance so dramatically that failure became inevitable. And that's the real story behind why 1940s locomotives never broke down. They broke down constantly, spectacularly, and expensively, proving that even the most advanced steam technology couldn't compete with diesel's fundamental advantages. The repair shops didn't hate these locomotives because they never needed repairs. They hated them because they needed repairs constantly, eating shop time and resources, while diesel locomotives just kept running. Don't forget to subscribe for more tales of engineering ambition colliding with mechanical reality. Here's another video I've specially selected for you. See you next time.